Good afternoon, all. I'm Angie Stevens, and I'm standing in for Rui Feo and Joe Kingham. This is the last session for the large systems stream, but we do have a keynote at 5 p.m. From Larry Strickland of Data Kinetics. Is the grass really greener? So it'd be nice if you can attend that. This session is from Steve Warren of IBM Poughkeepsie, and it is 9Q for the feedback, and it's a parallel Sysplex update. So please fill in the feedback at the end of the session, as it not only helps the speaker, it helps us at GSE to know what you want and what you don't want. So oh yes, questions. If you can add them to the chat, and if there's a point where I can interrupt Steve to ask, I will. Otherwise, he'll take them at the end. I'll relay them to him. So with no more ado, I'm going to hand over to Steve, and thank you very much, Steve, for doing this. You are. I'll hand over to you now, Steve.
Okay, thank you so much, Angie. Appreciate it. And I always love the GSE conference. I just feel that it's so valuable, and the amount of good information that they get out to our worldwide client base is just amazing. I would encourage you, if it's all possible, for you to attend the in-person workshop that they have usually in the November time period of each year. So, but this is just a great way for folks that can avail themselves, whether they can go to the in-person event or not. So thank you for that. I'll tell you a little bit about myself, and then we'll get started. So my name is Steve Warren. Like Angie said, I do work in IBM in Poughkeepsie, New York, across the pond from the UK. I am a STSM and a principal architect for a group called IBM Client Engineering for Systems. I spent the vast majority of my career in ZOS or ZOS development, and I currently work in this Client Engineering for Systems, helping clients embrace the very latest technologies on the Z platform or Z platform. I'll try to use Z as much as possible, but you know, these Yanks over here, we like to say Z is the last letter of the alphabet, so you'll have to forgive me if I sometimes say that. But with that, again, we welcome your questions. And for those of you who attended my first session today, which was what's new in ZOS 2.5, that was really a whirlwind tour, and I was talking motor mouth speed, and everyone's head was, you know, up in smoke. The idea of that presentation is just to expose you to all the things that are available in the release, and then maybe have it, you know, have what types of things you may want to dive into. This presentation, on the other hand, is a little more traditional. It'll follow the rules of what a good presentation hopefully is, and that is to not talk too fast and to not have information overload. So with that, you know, also my email address is right here. If you have any additional questions, feel free to reach out to me. I'm here for you, and not just for this 60 minutes that we're going to be sharing together. Okay, so with that, no further ado, let's go on and talk about parallel Sysplex. So there's lots of things we're going to talk about. Here is some of the agenda that we're going to be covering. We'll talk a little bit about the Z16 and how parallel Sysplex fits into that particular piece of hardware that was just introduced a number of months ago. We'll talk a little bit more about parallel Sysplex and its relation to System Recovery Boost. There's a lot of cool features in System Recovery Boost that have been added as part of Z16. There's also ones that are available in Z15, which we'll do a quick recap on. With a new level of hardware comes a new level of a coupling facility. We'll talk about, if you have a Z16, what new functions you can start to exploit on that Z16 as it relates to coupling facility functions. We'll talk about a Z15 function and that is still available, of course, in Z16, called CF monopolization avoidance, which is had a lot of folks with have a lot of excitement around. We'll talk about the new ZOSMF CFRM policy editor and how it really revolutionizes how you can administer your CFRM policies. and the cool functionality and complete replacement, and even more than complete replacement from the traditional batch utilities that you would use to modify those policies. And if time permits, we will also talk about the XCF Notepad enhancements as well before we wrap up for today. So that's kind of where we're headed today. And again, feel free to ask any questions. I'll try to stop and just ask Angie if there are any questions in the chat, okay, from time to time. All right, let's dive in to the IBM Z16. And with the IBM Z16, there are a couple of improvements that have been made that affect parallel Sysplex. And that is related to the coupling improvements that have been made. And you're going to see that both the short range and long range coupling links have had significant benefits. And you're going to see some pretty dramatic improvements in some of these cases when you're moving between a Z15, for example, and Z16. The first thing we're going to talk about here is the fact of coupling connectivity. And when a Z16 is introduced into a Sysplex, what does that mean for your capabilities in terms of the coupling between all of your systems? So let's talk first about the Z16. The Z16 has the same short range set of capabilities that were before, which is the ICA SR 1.1. That is still there. And what you'll notice in the Z16, we have something that is the Coupling Express 2 long range, as opposed to the traditional Coupling Express long range, which replaced a lot of the prior InfiniBand types of links that we had between various systems. So how does this all work? So if I have a Z16 and I need to use a Coupling Express long range. Again, long range is for extended distances that are greater than 150 meters, for example. In this case, I don't need to change cabling because the Coupling Express 2 long range card is fully compatible with the Coupling Express long range. So if I'm needing to communicate between my Z14 or Z15 and my Z16, I don't need to worry about that. I just have a new card which has additional capabilities. Some of those capabilities can be realized even if only one side is Coupling Express 2, and some of them can be better realized when both of the sender and receiver sides are both Coupling Express 2 cards. So again, let's just talk a little bit about connectivity. Just like previous generations, the Z16 can only couple with machines that are in the N-2 generations or newer. So that means that a Z16 can participate in a Sysplex with any of the Z14 models. So that's either the Z14 or the Z14 ZR1 or the Z15 T01 or T02. Okay, so older InfiniBand connections are not supported in any Sysplex, which includes Z16. Okay, so you have to use the cards for short range, the ICA SR 1.1 and the Coupling Express or Coupling Express 2 long reach. Okay, so that's a couple of things we need to know. So it's kind of business as usual here. So we always, a Sysplex, we only allow to have N-2 levels of hardware inside of in there. And so we have not changed that policy at all. Okay, so again, why do we use these different cards? Of course, they have different specifications. So again, if you're within 150 meters, so basically the distance of a soccer stadium from one end to the other, one goal to the other, you're going to be able to use the SR ones for long ranges, again, up to 10 kilometers unrepeated, or if you have a DWDM, you can go up to 100 kilometers. So Again, there's some the same general specifications are apply for both the short range and long range. Let's talk about the benefits at a high level. We're going to dive into each one of these in just a moment. So on the short range, we're going to see that there's a reduced service time. And you're going to see that there's been lots of efficiencies that are made on the existing card. Remember, your Z15s also may have SR 1.1s. And yet there have been some significant enhancements that have been made to have much better service time than before. And in addition, on the Coupling Express 2 long range, we've added more throughput. So we can push more data through the pipe than we could in prior generations in the same amount of time. So very, very cool. So let's dive into each one of these. So the first one is, let's talk about the short range latency improvements. So we have shorter CF service times, better coupling efficiency, and less coupling overhead. How did that all happen? Well, what happened is that they refactored a lot of the ICA SR protocol engines and the Z16 coupling related IO capabilities. And so using that exact same hardware. So the protocol engine and the IO capabilities have been greatly improved, whether it's hardware offload engines or the right protocol or removing round trips that are necessary to fulfill a protocol. The bottom line is we don't care so much about the details, except that we can say there's less overhead. And what's good about that is that not only that you have shorter CF service times, that you can actually impact and reduce potential cost savings in a parallel Sysplex environment, because the code is more efficient on the ZOS side, which means that you're consuming less CPU. So this is a win-win all around. You have less CPU consumption and you have shorter CF service times. So it's really a good news story. So again, you're going to improve the CPU synchronous and asynchronous service times. And so again, and you're going to see on the next chart of what that means in terms of the actual numbers, in terms of read and lock requests versus write and duplex write. We'll also just briefly mention that this is completely coexistent with legacy ICA SR connections. So in other words, if you have patches that were delivered to a Z14 or Z15, and you're pretty current with your ICA hardware patches, you can take advantage of all this technology. And what's great about this is that the ICA SR hardware can be carried forward and used on a Z16. Now, you can use the original ICA SR, or you can use the ICA SR 1.1. So you have a carry forward capability for this. Of course, the 1.1 is going to have significant benefits over the traditional one. All right. In terms of the coupling links performance, we've had some different numbers here, but we provide a 10% improvement for read requests and lock requests, and up to a 25% improvement for write requests and duplex write requests compared to the CF service times on IBM Z15 systems. So again, this has the consequence of being faster and less costly. All right, so that's all I'm going to talk about the SR coupling links. Let's talk a little bit more now about the Coupling Express 2, which is a new card. This is a technology upgrade. It also has improved link traffic management protocols compared to the previous generation of the CELR card. And so what this card provides is greater throughput at distance. It's able to push more data through the pipeline than it was before. Now, I make a tongue-in-cheek comment here. The speed of light has not changed. So obviously, once the data gets on the Coupling Express card, we can only go as fast as 186,000 miles per second, right? The speed of light in miles per hour. But we certainly can push more data through. And so you have significant, you'll see on the next chart that we show that there's a significant throughput. And again, those that have a stretched multi-site Sysplex at metro distances can definitely take advantage of this particular card improvements that we're able to push through more data. And how does that translate here? So again, 15% improvement when we compared a Z15 to a Z16, one running the Coupling Express long range versus the Coupling Express 2 long range. And you can see that the differences. Of course, as we always say, that your experience may vary. The amount of improvement will vary based on the distance, the workload, and the configuration. But you can see right now that besides the technology upgrade, there is a throughput increase of the amount of data that can go across the pipe. So very good. Now, in addition to those two improvements, it's always very important that we do our due diligence. And what we mean by that is that you need to make sure that all the required PTFs are installed on all the ZOS images before introducing a Z16 server into the Sysplex. This applies both to ZOS as well as to the coupling facility images. And so you need to make sure you're running current service. And I'm going to show you on the next slide what that looks like in terms of that. Now, if you want to run some of the Z16 exploitation, which means all of the new features that are on the Z16, you're going to need to install an additional set of PTFs. So let's just go right to that slide and talk about the PSP buckets and the fixed categories. So again, the PSP bucket has that information up at the top there, the upgrade and subset. But I like fixed cats, and if you use fixed cats a lot, you can have a quick reports that you can run to make sure that you have the requisite PTFs installed. So the required service, again, all of the fixes that are required to run ZOS on the Z16, you have to have those, and you're going to want to check to make sure that you have the necessary on all of your ZOS images to make sure that those images are compatible with Z16. If you want to exploit things that are on the Z16, particular functions that are of benefit to you, of course, you need to do the exploitation fixed cat, and finally the recommended service one is that you install these. They're not absolutely required, but they're highly recommended. So again, here are the 3 fixed cats you can use to install. Any questions on the Z16 and the updates to the ICR SR 1.1 and to the CE2 long reach, or about just hardware configuration?
There are no questions on the chat at the moment.
Okay, perfect.
Just a reminder to everyone, if you've got any questions, please type them into the chat and I'll relay them to Steve. Okay.
Very good. Thank you. Thank you. I appreciate it, Angie. Okay. All right. So let's go on to the next topic. And the next topic, let's talk about System Recovery Boost. So System Recovery Boost on the Z15, in my mind, was the flagship hardware feature on that machine. Besides, of course, the incremental performance improvements and many other great features on the Z15, I would say System Recovery Boost had the most big splash. It also had the most customer acceptance, and customers love it. And we're going to talk a little bit about review of System Recovery Boost technology. I might refer to as SRB also. And then the extending with the additional boost for Z16, of which one relates to parallel Sysplex. And we're going to talk about these a little bit because parallel Sysplex is a heavy exploiter of System Recovery Boost. So when we first introduced System Recovery Boost, again, the idea is to maximize the resources that are available to reduce the duration and impact of a planned and unplanned downtime. And so what we want to do is to basically increase the processing capacity for a short period of time during something called a boosting period to allow you to leverage more of the hardware on the system during those key points. And again, with zero increase to IBM software licensing costs. There's no hardware, additional hardware that you have to purchase for the base system recovery boost. There is something called system recovery boost upgrade. We'll talk about that just very briefly. But the idea is that I can now reduce disruptions, both at when I IPL and shut down an IPL, as well as something called recovery process boosts, which are used to accelerate parallel Sysplex recovery activities and workload restoration. So we're going to talk about, in particular, recovery process boosts, because recovery process boosts directly relate to parallel Sysplex. And now with the Z16, we're introducing more ways that you can maximize this. And again, there's no cost to use system recovery boost from a hardware perspective. And when you use it, your IBM software licensing costs do not go up. So because even though you have additional capacity, it's being reported at the original capacity. So let's talk about recovery process boost. We're here about parallel Sysplex, not necessarily just about any kind of system recovery boost function. So in Z15, we provided 4 capabilities with Hyperswap, with CF data sharing member recovery, Sysplex partitioning, and CF structure recovery. So what allowed this to do is for us to increase the capacity of the machine, and we'll talk about how that was manifested in just a moment, to allow you to have these actions take as little time as possible, because these are disruptive things that are occurring on your system, which are, you want to accelerate their completion, okay? And to allow backlogged, if some things are backlogged during that time period, for them to be able to have an expedited return to steady state. So a little bit about process recovery boosts as a recovery process boost. They are short duration boosts. They are at a maximum 5 minutes or less. They're 5 minutes or less in duration. They can apply, one boost can involve multiple LPARs that participate in that. For example, when I partition a member out of the Sysplex, there may be multiple systems. When I do a CF structure recovery, there may be multiple systems that are asked to participate in that. Any system in the Sysplex that needs to participate in a particular Sysplex recovery action can get a boost during that time. Now, per LPAR, I'm allowed up to 30 minutes of recovery process boost per day. That's on a per LPAR basis. Now, that is going to come in very important, and in a couple slides from now, we're going to talk about that and why that matters, and why it matters to someone that's interested in parallel Sysplex. Parallel Sysplex recovery boosts also can use both kinds of boosts, which we're going to talk about in the next slides, which are speed boosts and zip boosts. And so let's talk first about speed boosts. So speed boosts are really a way of taking a subcapacity machine model and running it at full capacity speed on the boosted image or images. So imagine if I have 2 systems that are participating in a Sysplex recovery action, and I have a subcapacity machine. As far as those LPARs are concerned, they're running at full capacity. That means that they are going to run at the maximum capability of the number of processors that they were assigned there. So that's very good. Full capacity and speed. The processor speed metrics will show the boosted GP processor speed, but it will not be reported as such. The GPs, so for LPAR, OS image and group capping, and again, SMF records for pricing purposes will have unboosted GP capacity. So through hardware instrumentation, we can see that there was a boost that took place, but in terms of capping or in terms of pricing, you will not see the change. They will remain they will look as if they're unboosted. So that's the first kind of boost. The second kind of boost was something called a zip boost. And this allows you to blur the distinction between general purpose processors and zip boosts and put them all together in one pool. So this is very, very useful when I'm doing a recovery action. I might have lots of zip engines that are available to me that I can't run because, for example, my parallel Sysplex activity gets dispatched on a GP. It does not get dispatched on a zip. So during a boosting period, those additional engines can be made available. What does that mean? Additional parallelism that allows me to push through more work on the system. Now, let's talk about the amount of zips that I can have on here. First of all, normally the way you can have something called reserved logical zips. Those images during a boosting period can automatically bring in those additional logical zip processors online during that period to fulfill a system recovery boost request. Now, in an IPL boost, many more engines can be brought in a recovery process boost, of which parallel Sysplex actions result in. At most, 2 additional engines can be brought in addition to the existing zip engines that you have running. Okay. Another thing to note is that SRB upgrade, which is an optional priced feature that allows you to tap dark engines, for example, that are on your system that are not even part of your machine model, for example, we can bring those online during temporary periods. And so system recovery boost, recovery process boost does not leverage those special SRB upgrade engines that could be brought online. So again, increased throughput in terms of being able to have engines running at a faster speed than they were before, and additional engines for increased parallelism. So both of those can be exploited. So now in the Z16 space, what additional boosts are there? Well, 2 of them are not related. I'll just mention them very briefly. One is called middleware region start and restart. There's one also for SVC dumps. So here's the problem. When middleware region is down, it's not processing normally, and therefore a backlog of work can be accumulated, right? When we have an SVC dump, parts of the system are non-dispatchable, which causes a delay in your workload. You can see that all of a sudden your workloads, you can have an increased amount of delays when a dump is being taken. And then lastly, in the parallel Sysplex space, hyperswap configuration load. So in addition to normal hyperswap processing, which is already on the Z15 eligible for a recovery process boost, we now have something called hyperswap configuration load. Configuration loads can be a very long and processor intensive process. And so what we want to do is to minimize that, because while a load is taking place, guess what? Hyperswap is not even available during that process. You are exposing yourself to not having hyperswap available. God forbid one of your DS8Ks has a problem during that time when you're doing a configuration load. Now, the odds of that are very low, but you know Murphy's Law, right? And so we want to make sure that when hyperswap is not available, we want to reduce that time to as small a window as possible. And so that's what hyperswap configuration load is providing for us. So with Z16, we now can specify for a given client which address spaces need to have a boost. And in Workload Manager, we're able to specify which ones should get a boost. So when we start that particular started task, we can actually give a boost during that time. Now, why am I talking about this? Because it's not parallel Sysplex, because it's going to play on the next couple of slides. After two slides from now, you're going to see why this is important. If I have middleware that takes a couple minutes to do, it's going to use recovery process boost time. Remember, you only get how many minutes? I'm going to go back a couple slides. You get 30 minutes of recovery process boost per day per LPAR. So if I'm using some of that time now for middleware, to start middleware, which is very important, I need to be able to start my middleware as quickly as possible. But I might also have a dump, which when SVC dump is taking place, I set a threshold limit of how large the dump should be before I actually want to kick off system recovery boost. So when a dump is about to be taken, there's an estimate of how large the dump is going to be. You can set the threshold for that. And if anything bigger than that, we're going to request a recovery boost. So, and then there's hyperswap load. So now let's go here. So again, we accelerate the configuration load with the expedited loading and reloading of that because we're running under a boosting period. So in this example, we have lots of things in addition to all those things in Z15, such as a Sysplex partitioning, such as CF data sharing member failures, such as hyperswap and others, right? All these things now are part of the recovery process boost. So let's just talk a little bit about this hyperswap configuration load boost, and then we're going to get down to the details of what this entails. So from the SRB perspective, we now have this new recovery process boost. You don't have to do anything in order to enable this. It's active by default. There's no criteria that applies to this. If you have recovery process boost time available for the day in your LPAR, it's going to take the boost if you have a load. And GDPS, CSM, or any other hyperswap manager that makes use of the ZOS hyperswap related service calls is eligible for this boost. Okay, now that we've talked a little bit about that, and we have at least 5 of the 7 actions for recovery process boost are Sysplex related, we need to now want to consider that maybe there's a chance that we could run out of recovery process boost for a given day. So IBM has provided a new capability that allows you to turn on or off recovery process boosting. So this is very useful. If I'm doing some kind of activity in a time period where you expect that the impact of that activity, while it would be a boosted activity, is not significant enough to use some of my boosting minutes per day, I can choose to disable that before I do that activity. For example, let's say I'm running on a machine that I need to restart a piece of middleware somewhere. And I know that when I restart that middleware, that I've set up Workload Manager to be able to that it's going to know that it wants to boost that startup of the middleware. But it's very minimally, it's going to minimally impact everything right now. I don't want to avail myself and take maybe 5 minutes of my 30 minutes away from my 30-minute total. I can choose to disable it, right? And so this again gives your client, it gives our clients more control over when they use recovery process boost. I can turn it off. Nothing will be boosted. So this is a concern. If you turn it off and then you don't have, now your parallel Sysplex, it turns it off for all of the things that are eligible for recovery process boost. Okay. When you're ready to turn it back on, you can invoke that proc again to turn it back on again. Okay. So this is just something you need to manage. And because parallel Sysplex items are 5 out of the 7 things that are eligible for recovery process boosting, we need to make sure that we are aware of that. Now, let's talk about the display command that we have. First of all, we have a display command which talks about boosting information. And a lot of new things highlighted in blue on the screen have been added to provide you additional information. And so we first now will tell you if the recovery process boosts are currently enabled or disabled. Before, they always were enabled, right? And now with that proc, they could be disabled. So in addition to the boost that is occurring right now, we'll tell you if it's enabled, and we will also tell you the boosting usage, and we'll tell you about which boosts you have enabled and how much time you have left for the recovery process boost. Now, what's interesting about this is that there's also SMF records, which will be cut that contain 3 different fields: actual, potential enabled, and potential. So this is very important. And let's talk about each one of these. When you look at these boosts, you're now going to see that you have an actual boost time of the actual amount of time that you have that you've actually boosted during the 24-hour period. The potential enabled boost time also adds in boosts that did not occur even though the boosts were enabled because there wasn't sufficient boost time available. So if I have if the actual boost time was 30 minutes and your potential enabled boost time is 35 minutes, maybe you might want to consider to use that proc to reduce what things are getting, when things are getting boosted and when things are not. And also then the potential boost time also adds in boosts that did not occur because boosts were disabled at the time, okay? So in other words, you're requesting boosts during times when boosting was disabled, okay? So more data available to you. The SE also has recovery process boosts that are listing more information and more details than before. So this is important when you're deciding which Sysplex actions you want to know. So the bottom line is, to learn more, click on the hyperlink here and you can get more information about System Recovery Boost. Okay, I spent a lot of time on that because I think that's a very exciting thing, System Recovery Boost, but lots of new controls to help you manage that. All right, let's talk a little bit about the new coupling facility level on the Z16. So on the Z16, there was a major refactoring of the code, which provides better processor scaling. Now, so a lot of folks we've seen that that when we had that you'll see in a chart on the next chart that once you start getting over a certain number of CF engines, you really were not getting much more throughput because the parallelism was not as good as it should have been. And so there was a lot of changes that were made to improve the parallelization of the data. So the bottom line is this underlined statement at the bottom, which says better internal CF scaling, vertical scaling. So it provides more CF throughput and capacity per CF image. And this minimizes the number of CF images to manage and connect. Now, if you already have several CF images, you don't necessarily have to consolidate with this new one and just add more engines to them. Because you need to have white space, of course, when you have peak workloads. But here's a good graph that illustrates what we're talking about here. The Z16 is in the green. As you can see, your mileage may vary, but the general practice of not trying to go beyond 9 processors for a single CF can now be relaxed. As you can see, we provide almost linear capacity growth as you add CP engines. So this is the Z16 compared to the Z15. So it's pretty dramatic. That green line is divergent from that purple line when you start to get to 9 CF engines. So of course, ideally, if of course no multiprocessor thing is like this, the ultimate would be a 45-degree angle, right? That says as I add one processor, I get the equivalent amount of capacity. So this is a little more flat than a 45, but it's still a very good curve that shows the capabilities of what we're trying to accomplish here by the increased capacity on a single CF. So again, this may change the way you think about how you create new images. You might want to consider just adding more engines to an existing CF rather than having a whole other LPAR that you need to manage. Let's talk a little bit about resilience in terms of lock record data and structure full conditions. So there's something called record data, which a lot of folks use for lock tables and data entries that it basically has this concept of special data that can be, up to the exploiter what they want to put in there, information about held locks, recovery information, other management information. And one of those folks that uses this pretty heavily is vSAM record level sharing, or RLS. What we do in this case is that we make RLS will try to make an attempt to update or create a record when they're doing just normal activity. What happens if the structure is full? Well, they will not be successful in updating that record entry because it's full. So the exploiter then is going to say, oh, I need to issue recovery or backup procedures to deal with that failure. Guess what that recovery and backup procedures try to do? They try to write record data. which of course is going to fail the same way the first time I tried to write record data. It's going to fail with a structure full condition. So what happens is it's kind of ugly. Manual intervention is required to recover. So it's an elongated outage. So now what we've done is we've allowed you now to reserve record data entries. An exploiter can require a number of unused record entries to exceed a given percentage of in-use entries. So what this basically means is that conceptually, I have a number of free entries are reserved. Now I tell you it's conceptual, but in how it's actually carried out is as if it's reserving those entries. So what's happening is a normal request can be failed with a structured full condition, but I still have a certain amount of reserved entries that I can still write record data in. So that is really good that I have this extra room for growth. And so I avoid this failure. Well, actually, it's a double failure in this case where I try to write record data multiple times. And so this VSAM RLS is going to be exploiting this capability. So let's talk a little bit about cache residency metrics. And so caches, of course, are typically very full, and that is something that is by design. We're using a cache structure because we want to maximize the data that's in the cache, and so we want to have the cache very full. But there comes a time at some point when you're writing data to a cache where I don't have enough room in the cache anymore, and something has to leave so that I can put this new item in the cache. But the problem is, which one do I remove? And so there's reclaim algorithms that help to make that determination. And of course, cache effectiveness is determined by the hit ratio. But there are not as many metrics as that some of the exploiters would like to have. For example, how long was the data in the cache before it got reclaimed? And some of these other things that are listed here. So for the sake of time, we won't go through all the details, but suffice it to say is that there's a lot more metrics that are now collected that our first exploiter DB2 with this particular APAR can now leverage and then improve their cache structure management. So this is a very important thing to have a more efficient caching of their cache structures within the coupling facility. And so, of course, DB2 with its DB2 data sharing groups exploits this particular set of technology. Okay, let's talk about another thing that's related to cache, and that is dealing with IFCCs, or something otherwise known as an interface control check. An interface control check is something indicates that an incorrect signal occurred on a channel path, right? So let's give a little history lesson. CF cache structure operations were idempotent many years ago, in which another way of saying that they're perfectly retriable. So we didn't have to accommodate for failures. Basically, if something failed, just redrive the request again. If it never made it to the CF, it will not be processed. If it did get processed, XCS will get back the same result. ZOS will get back the same result as the original request. However, over time, that idempotency has gone away, and requests to the cache structure architecture is no longer perfectly retriable in many cases. So, but the problem is that XCS doesn't necessarily know what to do. If I got an IFCC, do I retry it or do I not retry it? So to show it in a pictorial diagram, here's what happens. We make a request to and we get back an IFCC. What happened? Did we actually complete the task on the coupling facility, or on the round trip when we came back? That's when we had the interface control check. And so, so that would say it did get completed, but we couldn't get the result, or it never made it to the coupling facility to begin with, and we got an IFCC. Now there's a capability that allows us to basically have something called a retry buffer. And these retry buffers will cache requests that are not idempotent. And so what's going to happen is this. The CF is going to perform its operation. and it's going to put the results in the retry buffer before sending them to ZOS. So if ZOS gets an IFCC, it's then going to read the retry buffer. It's going to issue another request over probably another link to look at the retry buffer and say, hey, did that thing complete or not? If it did complete, I'm done. If it did not complete, I can simply redrive the request. So again, providing higher resiliency when I receive an interface control check. And last but not least, in the area of CF levels, we're going to talk about dynamic dispatch. For folks that have shared coupling facility, shared processors with their coupling facility, again, this is not a recommended configuration for folks that have production coupling facilities, but some folks will run in limited circumstances with shared processors. So we changed the default value for dispatching of being able to how does one coupling facility get control of that processor versus another coupling facility. And the way we dispatched it was something called thin dispatching, which was the most efficient sharing. Most clients said, hey, I don't want these other dispatching modes on. I want just thin. We made it the default value in VIP15, and in Z16, they are the only way for shared processors on a coupling facility. So just be aware that on the Z16, that is the only methodology that we can dispatch. I'm going to take a break right now. Are there any questions for any of the topics we've covered so far? Anything related to the Z16, the system recovery boost, or the CF levels?
Yes, there's a question from Phil, and it says, it would be nice to have control over which middleware tasks are eligible for recovery process boosting. For example, by WLM service class, not all DB2 or KICS instances require the same QoS.
Okay, well, I'm glad that Phil, you asked that question. The answer is yes. That's how you set it up in the WLM service class. So you picked our design point and perfectly. So you choose what middleware components get a boost. And in fact, middleware is in quotes, in air quotes here. You can pick any started task on your entire system to have eligibility for that boost. So it doesn't have to be just what we classify as traditional middleware like DB2, IMS, MQ, HICS, WAS, for example. They certainly can be part of it, but it's in the service class where you're going to be making that distinction. So perfect. That's exactly what we did, and that's how you are going to specify. Not all middleware gets a boost. In fact, none get a boost until you explicitly go into your service class and say which ones get it. Any other questions?
Right. There aren't any other questions in the chat at the moment.
Perfect. Okay, we're doing good with time here. I think we'll be right on time here. So let's talk the next thing about CF monopolization avoidance. And this has been around since Z15, but I'm going to talk about it again because a lot of folks are still not aware of this functionality. And the idea with CF monopolization avoidance is do not let one structure dominate the use of the coupling facility to the detriment of all the other structures. So the problem is that, of course, we have a finite number of tasks within the coupling facility to do its processing, a finite number of threads. And so if a CF requests targeting a single structure consume a disproportion of those tasks, the other targets starve. So when it happens, it's very, very painful. The good news is it doesn't happen a lot. So we have taken a couple of charts courtesy of Watson and Walker from last year that showed some very interesting behaviors that they have gotten, that they analyzed when they had a structure that was out of control, that was monopolizing a lot of the CPU resources of the particular coupling facility. So again, here, so each line here represents the sync response time for a different structure in a given CF. So each one represents a different structure. And you notice if one is really using a lot, then you can see all the structures are experiencing really bad service times during this bad interval, right? So other ones are adversely affected. So like, let's say the top one was the one that was the offending structure, the offending party that with the structure that's really monopolizing the resources. The other ones right below it follow almost exactly the same. They also have horrifically bad response times during that interval as well. So we're going to show you how we solve that problem. So the solution is that the coupling facility and ZOS are going to work together to manage the requests and to throttle down a guy that is a bad actor. Okay, so the CF is going to determine whether a given structure appears to be monopolizing. And so every single request targeted to a given structure is kind of like a way of saying, hey, is this guy behaving okay? The CF indicates whether the targeted structure is monopolizing if he is. Okay, so then ZOS will get that information, parallel Sysplex, and they'll do some processing. We're going to show you the next screen that they can potentially throttle that request down, so that allow other structures to run work as well. And you're going to see that it has a benefit in the most unusual way on the last diagram here. So managing the monopolized structures. Let's talk about this. Managing monopolized structure. I have the right now, I'm just starting my workload. I'm running a request. I'm sending requests to a particular given structure. And guess what? No problems. There's no monopolization. Business as usual. Now we come along, and after some period of time of infinite requests that we're sending, and of course, infinite is in air quotes. Of course, nothing's infinite, but there's no limit here. The CF says, you know what? Out of all these tasks, and I have the ones that are offending in yellow and the ones that in green that are not, this one structure seems to be taking up a very vast majority of our tasks. I'm going to be telling you, he gives back an indication to XCS, you know what, this guy's monopolizing. So what we'll do is we will monitor that for a little bit and determine if that is a repeated pattern. If it is, and we are now going into managed mode, we will then pick a number that's based on, the algorithms that within the system. They're going to pick a number N to throttle the workload down. They will have a message that comes out on the console. And notice the thickness of the bars. And I like to credit my good friend and colleague, Mark Brooks, who made a really good picture on this slide of this functionality. So the very thin means that it's very easy to transition between one of these not monitored, not managed, for example. It's a thin arrow going down. It's very easy to go from not monitored to monitored. It's a little bit harder to go from monitored to managed. And you can see by the thickness of the bars how difficult it is. In other words, you need to have it happen repeatedly before we're going to start doing it. So after a period of monitoring, we determine that the problem is not being alleviated. It's not just a fluke. We then will throttle it down to a managed number, N, requests coming from this particular ZOS to this particular CF. And then eventually throttle it down to 2/3 N and possibly even to 1/3 N. And in between these transitions, going from N to 2/3 N to 1/3 N, we'll be issuing this IXL 064I message in both directions of going from up and down. So the idea is we're going to reduce the amount of requests going to that particular CF structure. Now, here's the amazing thing. So this is very good. You notice that the troublemaking structure at the top there is the only one that was impacted. And after the throttling comes down, those other structures had very little impact to their response time. But this is very funny and a very interesting fact that actually even the offending structure, because there was not a lot of tremendous throttling and overuse of those tasks and running in parallel to that, even the offending structure received better response times So it's just kind of all the structures benefit from this particular CF monopolization avoidance. And so this is, again, thanks to Frank Kine and Cheryl Watson for allowing us to use a couple of their slides in this presentation. So one of the key things is that you have to make sure that you enable this on all of your systems. And so we'll talk about that in the next slide. But how do you enable it? So in 2.5, by default, it's enabled. On 2.4 and under, you will need to explicitly enable it, so or disable it. So in this case, CF monop avoid is the chicken switch. So on 2.5 and on 2.4 and lower, you have to explicitly say enable. On 2.5, you have to explicitly say disable, because by default it is enabled. So again, this is either done through at IPL through your couple XX functions statement, or via dynamic set XCF functions command to turn it on or off. Now, this is a very important point. Each individual system does its own management. So if I don't do this on all the systems in the Sysplex, I'm not really going to be getting a lot of benefit. So imagine one structure on multiple systems as accessed by multiple systems. If I'm only throttling down one system's talk with that structure and not everyone else's, CF monopolization avoidance is not going to be working optimally. So you really need to enable this on all the systems in the Sysplex for it to really account for. But I'm going to tell you right now, we've had very, very positive comments with CF monopolization avoidance. So I would highly recommend that you investigate this, even for if you're running on 2.4, and even if you're running just on a Z15, this capability is there to enable and to avoid this painful response when you have structures that are monopolizing the coupling facility. All right, the last major topic I'm going to talk about in our time here is just the CFRM policy editor. And just to talk a little bit about ZOS software Sysplex management. So ZOSMF, of course, provides a very modern interface to manage your ZOS. And one of the plugins or tasks that is in the ZOSMF functions is something called Sysplex management. And that in the first release, they allowed you to graphically view your configurations, such as coupling facilities and LPARs and CF connectivity details. So you could look at things like this and see your entire topology of your system, be able to drill down and look at individual structures. A very view-centric system, very useful. And then in about a year or so after that, we provide the ability to support commands, things like rebuild, duplex, restructure, switch and a primary and alternate couple data set, deal with path and stuff like that. And so in this picture, you can see that we had the set capabilities. The set capabilities provide a lot of great functionality that allow you to even look at all the commands that were issued from a historical purpose across IPLs. The data is hardened, even to allow you to preview the command before it actually is issued, because you may not trust what it did at first. Then you can check a box and say, I don't need to be previewed again. I trust what the Sysplex management plugin is doing. So there's lots of write capabilities that were made. And now what we're adding in ZOSMF Sysplex management CFRM policy editor is a way of comprehensive ways, ease of use for being able to provide policy editing, which in essence can replace the IXC MIAPU batch utility. I know we're close to the bottom of the hour here, but I'm just going to take a couple minutes to go over, and I hope that this will provide some additional benefits. So just bear with me a couple minutes, and we'll be done with the slides. So what we did is we provide a user interface in ZOSMF that allow you to not only do policy actions like create, delete, rename, and activate, but allow you to actually modify all the fields, doing things like bulk editing of structures. So I'm going to just show you a couple examples here. So here's an example of getting into the CFRM policy editor. And you can see here, once I click on a particular Sysplex, and I can now right click on the Sysplex and look at CFRM policies. I then will have a list of administrative policies of which I can modify. And then I can go into and actually view, like, for example, I can add a structure here. and I add a structure, you notice that I have pull downs for all the fields. I don't need to remember syntax or remember which job had the one that I wanted to. I can get just this right here. I can define my preference list. I can do anything you can do with the IXC MIAPU batch utility. Okay, so I can add the structures. I can also bulk edit structures. So in this case, I can select multiple structures. And then after I do a multiple structures, I can then say, I want to increase in an absolute sense the size, or I want to change the size of these structures to an absolute value of size. So I want both of the structures, or 5 structures I selected, to all have, 100 megabytes each. Or I can say relative. And if I click on relative, it'll say I want to increase or decrease what each one of those structures are by 10 to 20%. On both of these functions, you cannot do with the IXC MIAPU command. So this is actually exceeding what the batch utility does. In addition, we allow you to have a REST APIs that allow you to manage your CFRM policy remotely. So I can list the administrative policies. I can do all kinds of different functions through REST APIs. And I just issue a put to this particular, for example, resource, and it gets back JSON data that says it's completed. Of course, because ZOSMF supports the Open API standards, or Swagger, you can actually test them out on your system before you actually activate them. And you can see the programming guide for more details. You can also export your CFRM policies to a data set or file. So that's very interesting. So you can actually export that way. You can also do something called bulk copy structures, which allows you to copy multiple structures. And so you identify which structures, you can specify the copy name, and you can apply it. So it's very simple to do that. And it shows you here again, after copying the structures, the new structure names are there. I can compare 2 CFRM policies together to see what was the difference between one of them. And, in this example, I'm seeing that duplex was a different option for some of them than on the other one. And lastly, I can not only export to a data set, I can actually export in CSV file format, such that it can be imported into something like Excel to be able to look at my definition. So this is useful for people that want to generate reports of all their structures and be able to look at it and be able to sort and organize how things are organized on their system. So with that, I'm just going to leave you with that. So we're a couple minutes past the hour. I have a couple slides in here on Notepad enhancements. So again, Notepad is a unauthorized way of using basically list structures. And I won't go over the review of here, but I will just mention very good in terms of enhancements. Exploiters can now dynamically modify the size of their notepads. You could never do that before. And eliminate manual intervention when to recover when a host coupling facility is gone. So when the host coupling facility is gone, it'll behave the same way as traditional list structures, and eliminate that intervention to recovery a notepad. So that's all I have right now. And so with that, are there any questions that you may have? Additional questions that have been asked?
There are no more questions in the chat. Has anyone got any questions? I don't think there's anything, Steve.
Okay, great. So we really would appreciate your feedback. So if you would take a moment, you can scan the QR code on your screen right now. You can go to this website, or you can just go to the conference website, and you can provide us valuable feedback to let us know what you thought of the sessions. Give us some suggestions. Again, my email address, swarren@us.ibm.com. I'm here to answer your questions. So if you have a question to ask, feel free to engage with me, and I will be happy to give you more details about anything that I talked about in this session today. So
that was a great session, Steve. Thank you so much for talking to us this afternoon. I'd also like to thank all of you for attending the Large Systems stream at this virtual conference, and hope to see you at our in-person conference in November at Whittlebury Hall. So until then, thank you all. And thank you, Steve. Bye.
bye-bye now.